All right, class. Sorry that I am not there in person to do this lecture, but I've got to be off in DC. And so here's a fun video lecture for you guys. You don't get to see my smiling face, but you get to hear my smiling voice. So, first of all, how feels everyone? Awake and ready. Ready to what? Have fun and enjoy. Okay, so let's have fun and enjoy. So last time what we should have gotten to is we should have been able to do the derivation for the entropy expression for ideal gases. And that's the expression that you see here. And again, I want to emphasize this is just for ideal gases. So it's just like the ideal gas law where you have a special equation that you use to get properties for ideal gases. Same thing here. It's a special equation that we use to get properties for ideal gases. It's just that the property that we see here is the property of entropy. And so this equation, again, only applies for ideal gases. Only ideal gases, 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 only ideal gases. Okay, so anyway, here's the expression for entropy or change in entropy for an ideal gas. Now it turns out that a lot of times, instead of calculating the change in entropy, a lot of times we actually know that the change of entropy is going to be 0, or we want to see what happens if that change of entropy is 0. Because as we'll find out later, it turns out that when you have no irreversibilities and when you have no heat transfer, you have to have no change in entropy. And so a lot of times it just turns out that we want to know what's going to happen to the temperature if a process is isentropic. Isentropic is just like that term isothermal, iso meaning same, entropic meaning entropy, so same entropy, isentropic. So, isentropic. If you have a process that's isentropic, then you know that by definition S2 minus S1 has to equal 0. That's what it means for something to be isentropic, no change in entropy. And if S2 minus S1 is equal to 0, then what that means is that 0 is now equal to S naught of T2 minus S naught of T1 minus R log P2 over P1. So it turns out that if we do a little bit of mathematical manipulations here, we're going to be able to derive an expression that gives us a little bit of a shortcut that we're going to use a little bit later. And it's actually going to finally make sense what a couple of those columns in table A22 actually refer to. All right, so let's take this expression and let's solve it for the pressure. So if you move these guys over to the other side of the equation, divide by R, and then take it to the exponent because you have this logarithm right here, what you end up with is this expression that we have here. Okay, so P2 over P1 equals exponent of S naught T2 over R minus S naught of T1 over R. Now, if we do a little bit more manipulation, we end up with this new expression here because when we subtract exponents, it's the same thing as dividing by a number taken to that exponent, right? And so that's where we get this expression here from. So, well, the big thing to notice here is that this stuff on the top is a function only of temperature 2. And this stuff on the bottom is a function only of temperature 1. And so what that means is that now our pressure ratio, P2 over P1, can be related to a temperature ratio. Not temperature exactly, but something that's related to these temperature values. And so what we can do now is, since this whole kind of top expression here is just a function of temperature 2, just for shorthand, what we can do is we can calculate that expression. We can calculate e raised to the power of s naught divided by r, and let's just call it something else. Let's call it p sub r. Okay, and that's just the shorthand notation that we use, is we call that p sub r. And since it corresponds to temperature 2 and state 2, we'll call it p sub r2. And on the bottom, again, that's the same expression. It's just now related to temperature 1 instead of temperature 2. And so we can calculate that expression. We can take S naught divided by R, and we can raise e to that power, and then we'll just call that p sub r. And it's p sub r1 because it's related to T1. And all we're doing here is just using a shorthand notation. That's it, okay? And the idea here now is that when you have an isentropic process, and this only applies when you have an isentropic process, the pressure ratio, P2 over P1, is going to be equal to the ratio of these PR values, where those PR values are temperature dependent. And so what this means is that you can quickly use the pressure ratio, P2 over P1, to find temperature through these P sub R values. Let me give you a quick example just to kind of see how this might work. All right, so here I've written out an example, this is actually an example that will become fairly common as we move forward in the class. So let's say that you have an isentropic turbine. Air enters this turbine at 1300 Kelvin and 10 megapascal. So we have two properties at the inlet, which means we can get all other properties. We also know that air is an ideal gas. And since it's an ideal gas, this equation that we've just derived, which applies to ideal gases, is going to be valid. So air enters at 1300 Kelvin, 10 megapascal, and it exits at 300 kPa. Now this is actually a very common situation where you would know the inlet temperature and the inlet pressure of the turbine because you've designed a jet engine or a natural gas power plant in order to function at certain temperatures and pressures. And then you also have a known exit pressure on the backside of the turbine because the turbine is designed to cause a certain amount of pressure drop. And depending on what you're linking the turbine to afterwards, that might dictate what that pressure is going to be. So it is a very common scenario that you would know the inlet conditions to the turbine and you would know the exit pressure. That's a very common scenario because that's how things tend to be designed. Okay? And then you might want to know the exit enthalpy because you might want to know how much work output the turbine is giving you. So let's say we want to determine the enthalpy here. Let's apply this equation that we just derived and see how it goes. So I have now added in that equation let's see what we know here. First of all, do we know pressure 1? Yes, we do. Do we know pressure 2? Yes, we do. Do we know P sub R1? Well, I haven't actually shown this to you yet, but this is in table A22. Remember I said there's those two columns, P sub R and V sub R, that you should not use until later in the semester. Well, now is later in the semester, and this is when we're going to start using them. Those columns only apply for when you have an isentropic process. And here we have an isentropic process. Okay? So when you have an isentropic process, we know that the pressure ratio is equal to the ratio of these P sub R values. Okay? So P sub R is a function of temperature. So if we know temperature 1, we should be able to get P sub R1. And here we know temperature 1. Okay? So you can just look in table A22, go to the 1300 Kelvin row, and in that 1300 Kelvin row, one of the columns is this P sub R value. And if it were at 1305 or something that you didn't have a row for, you would just interpolate like you do for everything else. But we're just going to use that column, that P sub R column, and since the whole table A22 is listed by temperature, as long as we know the temperature, we can figure out where that P sub R value is. So that means we can look up this P sub R value out of table A22, and now all we have to do is solve for P sub R2. And once we know P sub R2, we can find where it is in table A22. And then we can use that spot in table A22, whatever row it's on, and you might need to interpolate in order to find it. But whatever row it's on, after you interpolate, you can use that to figure out H2 and T2 and U2 and whatever other temperature-dependent properties you need. That's actually all of them. There are no other temperature-dependent properties. Okay? So all it is, it's sort of a quick way, instead of having to go through the entire entropy equation for ideal gases, all we need to do instead is just use this quick little shorthand. And again, it only applies for isentropic situations. And it's just one thing that saves you a little bit of a step, just a little bit of a simpler calculation than going to the whole isentropic, or sorry, not isentropic, but the whole ideal gas entropy equation. Okay, so that's the shorthand notation for when you know the pressure ratio in an isentropic process. But it turns out that there's actually some situations where instead of knowing the pressure ratio, you actually know the volume ratio. And that actually shows up especially in internal combustion engines. You might have a displacement volume or a compression ratio that tells you what the ratio of volumes are during the piston cylinder movement process. And so let's do a very similar expression, but do it for known volume instead of known pressure. Okay, so again, focusing on isentropic processes here, we know that the pressure ratio, P2 over P1, is equal to this P sub R over P sub R. And P sub R, remember, was just a shorthand notation for some temperature-dependent stuff that came out when we had an isentropic relationship. All right, so using the ideal gas law, what we can do is we can say pressure, if PV equals RT, then pressure equals RT over V. So P2 is RT2 over V2, and P1 is RT1 over V1. All right, so I copied these P sub R values over to the other side of the equation again. And what we're going to do now is we're going to solve for V2 and V1. Okay? In particular, what we're going to solve for is the ratio V2 over V1. And if you do a little bit of algebra, what you'll find is the following. So the R's are going to cancel out, and what you end up with is that V2 over V1 is equal to T2 over PR2 over T1 over PR1. And if you don't believe me, just take a second and do the algebra to make sure that you figure that out for yourself. One thing to keep in mind is that the V2 up here is in the denominator, and since it's in the denominator, you actually have to flip everything upside down. Okay? But anyway, if you do some algebra, I'm going to trust that you can do that. You'll find this expression that I have down here in black. Now, one thing I want you to notice here is that this top is temperature 2, which is obviously dependent on temperature 2, and PR2, which is also dependent on temperature 2. So this entire numerator depends on temperature 2. And this entire denominator depends on temperature 1. Okay? And so what we're going to do is we're going to do another shorthand little trick here, is we're going to define this ratio, temperature over P sub R, as V sub R. Okay? And so now what we have is that V2 over V1, the volume ratio, is equal to VR2 over VR1. All right? Where VR is dependent only on temperature, and VR2 would then be dependent only on temperature 2, and VR1 is dependent only on temperature 1. Okay? And now we have the exact same scenario that we had before for pressure. What we can do is we can relate a volume ratio to something related to temperature. And we can put these things in the table. And so these guys are also in table A22 right next to the P sub R column. And so I could do another example if you want, but it's basically the same thing. Like let's say you had an internal combustion engine with a compression ratio of 8, so that you knew that V2 over V1 was 1/8. Then you would know this ratio, and if you knew the inlet temperature, you just solve for VR2 and use that to figure out the energy at the end. Okay? So these are the isentropic relationships for ideal gases. Again, they apply only for isentropic processes, and they apply only for ideal gases. Okay, and all they are is a little bit of a shorthand. Instead of having to go to the full entropy equation for ideal gases, it allows you to kind of skip a little bit of a step and just go straight to the table. All right, so one last thing before I finish this little video here. Question: what if you have constant specific heat and an isentropic process? Remember, specific heats are never truly constant. They vary with temperature, and that's why I say never really use this constant specific heat. Always just use table A22 in order to figure stuff out. But just for the sake of showing you something that may or may not be interesting to you, let's ask the question, what if you could assume a constant specific heat? So what if the temperature changes were reasonably small, small enough that the specific heat was pretty much constant? Well, the entropy equation for ideal gases with a constant specific heat is this, which you should remember from last time. We have both equations here. One, entropy is a function of temperature and pressure, and the other, whoops, made a mistake, give me a second. There we go. The other is entropy change is a function of temperature and volume. So, if you have an isentropic process, well, then S2 minus S1 is going to be equal to 0. And I'm actually not going to do the full derivation and show you all the algebra, because I'm going to trust that you can do algebra on your own if you really care. But keeping in mind these couple of rules that I've just written here, Cp over Cv is defined as K. Remember, that's the definition of K. It's the specific heat ratio. Cp equals Cv plus R. That came from the ideal gas law. You can check your notes from when we first started talking about ideal gases if you really want to verify it for yourself. And then if you use those two expressions on the left and do a little bit of algebra, you can derive these two expressions on the right. Cp equals Kr over K minus 1, and Cv equals R over K minus 1. So if you use these things and you play some algebra games, what you can eventually get down to is the following expression. P2 over P1 equals V1 over V2 raised to the K power. Now, if you really want to see the derivation for where that comes from, you can check your book. It's in there. It's not very hard to follow. It's just a little bit of algebra. But the key thing here that I want you to recognize is that if you rearrange this expression a little bit, what you end up with is this. P1 V1 to the k is equal to P2 V2 to the k. And that's something you should recognize as the polytropic expression. You remember back earlier in the semester I said, there's this thing, this polytropic relationship. It just turns out that PV raised to some power turns out to be constant for some reason that I can't get into yet, but I'll tell you about in about 10 weeks. Well, here it is. Here we are 10 weeks later, and here's where that expression comes from. It turns out that if you have a constant specific heat, so you have a temperature change that's small enough to assume a constant specific heat, and you have an isentropic process, then you end up with this polytropic relationship. P1 V1 to the k equals P2 V2 to the k. And so that's where this whole polytropic thing comes from. Again, remember, I said never, ever, 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 ever assume this unless you're told. And you should still just not assume this because this is really requires a few assumptions, in particular this constant specific heat assumption, which isn't really a great assumption. But this is just, I just want to derive this expression real quick just to show you where that polytropic expression came from, because this is where it came from. It's this isentropic process with a constant specific heat. So that is all we have for isentropic processes. So I hope this lecture was great fun and that you were ready to have fun and enjoy.